Hello, discrete math fans. Now we're going to talk about the language of sets. We want to think of a set as a collection of elements. Now, in our examples, the elements will be numbers, but we want to keep in mind that elements in a set can be anything. They can be functions, matrices, vectors, strings of letters, or they can even be other sets. We're going to use something called the set roster notation to describe sets. For example, we'll put 1, 2, 3 inside these braces to denote the set that contains the numbers 1, 2, and 3. Now there's no such thing as being in a set twice. You're either in or you're not. It's like being in a class. You can't register for a class twice. You're either in the class or you're not in the class. So if you were to write the set 1, 2, 2, 3, what we really mean is just the set 1, 2, 3. If we have a set that's 1, 2, 3, this guy right here, then we'll use this notation. 2 is an element of S. That indicates that 2 is a member of the set S, or that 2 is an element of S. So that little symbol there, this guy right here, means is an element of. We'll write 4 is not an element of S, and this is how we're going to write it. Sometimes if a set is really big, you can use what's called an ellipsis to denote some missing elements. Okay, so you can write 2, 4, 6, 8, 98, 100 to denote the set of all even positive integers up to 100. And when you use a ... it's very important that it's totally clear what the missing numbers are. Also, the order of elements in a set is unimportant. So the set with 2, 1, 3 and the set with 1, 2, 3 are the same set. Just like when you come to class, the order of arranging people in the room is not going to affect who's in the class. Finally, we have something called the Axiom of Extensionality, and it says that the set is completely determined by what's in the set, not the order that they might be listed or the arbitrary fact that you might list an element more than once. So only being in the set or not in the set is what matters. Okay, that's all for now.